Today I am going to explain about the spectroscopic methods. Actually, this is a vast subject that much detailed information is not required for food analysis. So, I will explain it in brief. What is spectroscopy? Spectroscopy involves the interaction of light with the matter to measure the concentration and structure of the compounds. It is an analytical technique used to determine the composition, quality and safety of the food products. It involves the interaction of the light with the matter, allowing scientists to identify and quantify different compounds in the food samples. There are several types of spectroscopy used in food analysis. Ultraviolet visible spectroscopy. It quantifies compounds that absorb UV visible such as proteins and the colorants. Applications are the quantification of the pigments like keratids, anthocyanins, etc. and detection of the food colorants and the synthetic dyes, and analysis of the vitamins, and monitoring oxidation and the degradation of the fats and oils. Next one is the infrared spectroscopy. It identifies the functional groups and the molecular structures, and it also identifies and quantifies the proteins, fats, carbohydrates, and detection of adulterants in oils and dairy products, and analysis of moisture content and the functional groups in the food. And it also monitors the food spoilage or the oxidation process. Fourier transform infrared spectroscopy provide detailed molecular fingerprints, and atomic absorption spectroscopy measures the metal concentrations and detection and quantification of the trace metals like iron, copper, zinc in the food and the beverages, and monitoring the toxic elements like lead, arsenic, mercury, and the quality control in food fortification process like iron in cereals, is calcium is there in the milk, etc. Inductively coupled plasma optical emission spectroscopy analyzes the trace metals and elements. Accurate determination of the trace and the ultra trace elements in the food samples, detection of the heavy metals and the mineral content in the food and water, and analysis of the dietary supplements in the fortification level. And there are also some other spectroscopic methods like nuclear magnetic resonance spectroscopy that gives the detailed structural elucidation of the complex molecules like lipids, carbohydrates, proteins, and determining the food authenticity like origin of wine, olive oil by fingerprinting detailed regions, and analysis of metabolites in the monitoring fermentation process, and quantification of the minor compounds like organic acids, amino acids, sugars, etc. And other one is the Raman spectroscopy. It helps in identification the molecular composition in the complex food matrices, and detection of the contaminants and adulterants, analysis of the carbohydrate structure, and monitoring the fat crystallization and protein folding during the food processing. And others are the fluorescence spectroscopy and X-ray fluorescence. Fluorescence spectroscopy helps in detecting the food contaminants like mycotoxins, pesticides, and polycyclic aromatic hydrocarbons, and it also helps in monitoring of oxidation in fats and oils by detecting secondary oxidation products, and detection of the natural fluorescent compounds in food like vitamins, that is riboflavin, phenolic compounds, and chlorophyll. And X-ray fluorescence spectroscopy is used in determination of the mineral content in the food, that is calcium, potassium, etc., and detection of a heavy metal contamination like lead and cadmium, and quality control in food packaging materials by analyzing the elemental composition. These all are same. Every spectroscopic method plays a crucial role in the food analysis. They give the rapid and the accurate determination of the chemical composition, quality and the safety of the food products. Everything is same. These are the several lab spectrophotometers: fluorescence spectrophotometer, near infrared spectrophotometer, ASFTIR, and portable Raman analyzer. Now coming to the mass spectrometry. Mass spectrometry is often coupled with the chromatographic techniques, that is gas chromatography with mass spectrometry and liquid chromatography with the mass spectrometry, for detailed molecular analysis of the food components, contaminants and the residues. And it is used for the identification of the volatile and the semi-volatile compounds like the flavor, aroma of the compounds. Now coming to the titrometric methods. These are also known as volumetric analysis. This involves some measurement of the volume of a reagent required to react with a sample. That is nothing but to determine the concentration of the unknown substance or the analyte. And in this there are different types of titrometric methods, that is acid base titration, which determines the acidity or the alkalinity of the food. Acid base titrations are used to determine the concentration of an acid or base by neutralizing it with a titrant of known concentration. An acid reacts with a base to form the water and a salt, and the end point is typically indicated by the pH sensitive indicator that changes the color. The titration curve shows a sharp pH change at the equivalence point, and the common examples include the titrations of hydrochloric acid with the sodium hydroxide. And acid base titrations are widely used in the laboratories for testing water and food products. This is the acid base titration. This is the analytical procedure used to determine the concentration of the acid or the base. The basic principle of the acid base titration is nothing but the neutralization reaction between the acid and the base. And here the acid and base gives rise to salt plus water. Here the apparatus used are the pipette, Allen-Meyer flask, and this is the indicator, burette. This is the analyte, the solution of the unknown concentration of the acid or the base that is being titrated. And this is the burette, it consists of the titrant, the solution of the known concentration that is gradually added to the analyte. Indicators used here is phenolphthalein, turns pink in the basic solution and colorless in the acid solution, and methyl orange turns red in the acidic conditions and yellow in the basic solution. With this pipette, we will transfer the analyte solution. This Allen-Meyer flask is used where the titration reaction takes place. Here, a known volume of the analyte is measured using a pipette and placed in the flask. A few drops of the indicator is added to the analyte solution. The titrant is added slowly from the burette to the analyte. While adding, we have to shake the flask to mix the solution. When the titrant is added, the acid and base reacts to neutralize with each other. Then the solution reaches the equivalence point, where the number of moles of hydrogen ions, that is H plus, will be equal to the number of moles of OH minus ions from the base. At this point, the indicator will show the color change. The end point is where the indicator changes color. This color change signals that the titration is complete. We can see that this is the initial reading of the burette, and we will release the solution or the titrant drop by drop into this analyte. After some time, we will see the final reading. Here, the volume of the titrant added from the burette to reach the end point is carefully recorded. We will see the reading of this. We repeat this titration 2 to 3 times for accuracy, and the average volume of the titrant is used in the calculation. The concentration of the analyte can be determined by the moles of acid is equals to moles of base. The formula is given by the M1V1 is equals to M2V2, where M1 and M2 are the molarity and the volumes of unknown and the known values. Molarity is nothing but the moles of the solute per liter of a solution. Volume is the amount of titrant or the analyte used in the titration process. The applications of acid-base titration is, it is used to determine the purity of the chemicals, and this titration helps in measuring the acidity of the food products like wine, fruit juices, etc. Complexometric titrations. These are the type of titrations that uses a chelating agent such as EDTA to form a complex with the metal ions in solution. The chelating agent binds to the metal ion in a 1:1 ratio, and the end point is typically indicated by a color change from a metal ion indicator complex. These titrations are used to determine the concentration of the metal ions in solution, including the calcium, magnesium, and other multivalent ions. The pH of the solution must be carefully controlled to ensure the selective binding. A common application is water hardness analysis. Next is the redox titration. Redox titrations involves a reaction between an oxidizing agent and a reducing agent, where electrons are transferred between them. The end point is detected by a color change, often using an indicator or potentiometer. These titrations are used to determine the concentration of an unknown substance by using a known redox agent. Common examples include titrations with the potassium permanganate or iodine. They are widely applied in determining the concentration of oxidizable or reducible species, such are iron or hydrogen peroxide. Redox titration determines the content of oxidizing or reducing agents. Iodometric titrations is a type of redox titration that involves the use of iodine as a titrant or the analyte. In these titrations, iodine is either produced or consumed in a reaction, and the end point is typically detected using a starch indicator which forms a blue complex with iodine. This method is commonly used to determine the concentration of oxidizing agents like chlorine or copper by reducing them to their lower oxidation states. And iodometric titrations are highly sensitive and precise, especially for compounds that can be quantitatively oxidized by iodine. They are widely applied in the water quality analysis and the pharmaceutical testing. Iodometric titrations used for the analysis of the compounds like vitamin C, that is ascorbic acid. Next, coming to the enzymatic assay, which uses specific enzymes to react with the target compounds, and later on it is followed by the spectrophotometric measurements. Glucose oxidase method is used to measure the glucose. The glucose oxidase method is used in the food industry to measure glucose levels in products like juices, honey and the dairy. And glucose oxidase catalyzes the oxidation of glucose to gluconic acid and hydrogen peroxide, with the latter being measured for quantification. This method is highly specific for glucose and helps in quality control by ensuring correct sugar content and monitoring spoilage. It is also used in food packaging to reduce the oxygen level, preventing microbial growth. This method is accurate, simple and widely adopted for both testing and preservation. In food industry, a lactase assay measures the activity of lactase, an enzyme that breaks down lactose into glucose and galactose. We know that the lactose breaks down into glucose and galactose. This assay is crucial for producing lactose-free dairy products by ensuring sufficient lactase activity for complete lactose hydrolysis. This method typically involves incubating lactose with the enzyme and measuring the resulting glucose using glucose assays or spectrophotometric methods. It helps monitor enzyme efficiency and optimize production conditions. And lactase assays are essential for the quality control in producing lactose-free milk, cheese and other dairy products. Lactase assay used to measure the lactose. Next, coming to the electrochemical methods. In this, it measures the electrical properties related to the concentration of the analytes. pH meters are essential in the food industry for measuring the acidity or the alkalinity of the food products to ensure safety, quality and the taste. They are used in processes such as fermentation, cheese production and beverage testing to maintain consistent pH levels. Accurate pH monitoring helps to prevent the spoilage and ensures the stability of the preservatives. The meters are often used in both production and the quality control stages, providing fast and reliable measurements. Maintaining the correct pH is crucial for the regulatory compliance and consumer safety in the food processing. Ion selective electrodes (ISE) are used in the food industry to measure the concentration of the specific ions such as sodium, potassium, calcium or chloride in products like dairy, beverages and the processed foods. These electrodes work by responding selectively to a particular ion in the sample, generating a potential difference that correlates with the ion concentration. And this provides rapid, accurate and non-destructive analysis, making them ideal for the quality control and monitoring the nutrient content. They are widely applied in salt content determination and the electrolyte analysis, and it helps to ensure the food safety, nutritional balance and the product consistency. Next is the fluorometry, measures the intensity of the fluorescent light emitted by a sample used for detecting the specific compounds or interactions. Fluorometry in the food industry used to detect and quantify compounds that fluorescent such as vitamin, proteins and contaminants. By exciting these compounds with light and measuring the emitted fluorescence, highly sensitive analysis can be performed even at the low concentration. And this technique is applied in monitoring food quality, detecting adulteration and measuring the spoilage indicators like microbial metabolites. It is commonly used for the vitamin analysis, example riboflavin, and ensuring compliance with the nutrients labeling. And the fluorometry offers quick non-destructive testings with a high precision, making it a valuable tool for the food safety and the quality control. Now coming to the microwave digestion. It is a process in which the microwave radiation is used to heat a substance and decompose it, allowing it for the analysis of elements in the various sample matrices. Microwave digestion is used in the food industry to break down complex food matrices into simple components for the elemental analysis, such as determining trace metals or the minerals. This technique uses microwave energy to rapidly heat and pressurize the sample in acid and speeding up digestion and ensuring complex breakdown of the organic material. It is commonly applied in testing for contaminants like heavy metals, example lead, cadmium, and verifying nutrient content. And microwave digestion offers faster, more efficient sample preparation compared to the traditional methods. It is essential for accurate and reliable elemental analysis in food safety and the quality assurance. And the nuclear magnetic resonance NMR spectroscopy means it provides detailed information about the molecular structure and dynamics of the food components. Next is the colorimetry methods. This involves the measurements of the intensity of the color produced by the chemical reaction. Phenol sulfuric acid method measures total carbohydrates. The phenol sulfuric acid method is used in the food industry to determine the total carbohydrate content in various food products. This colorimetry method involves hydrolyzing carbohydrates with sulfuric acid, followed by the addition of phenol, which reacts to produce a colored complex. The intensity of the color measured spectrophotometrically is proportional to the carbohydrate concentration in the sample. It is particularly useful for analyzing sugars and starches in the products like syrups, juices, and the baked goods. This method is valued for its simplicity, sensitivity, and ability to provide quick results for quality control and the nutritional labeling. Biuret method that measures the protein content. The biuret method is used in the food industry to measure the protein content in the various food products. It relies on the formation of a blue complex when proteins react with copper ions in alkaline solutions, especially in the presence of biuret reagent. The intensity of the blue color measured spectrophotometrically is proportional to the protein content in the sample. This method is widely used in analyzing dairy products, meats, and the plant-based foods to ensure quality and compliance with the nutritional labeling. The biuret method is favored for its simplicity, reliability, and ability to produce accurate result in protein quantification. Gravimetry methods. This involves measuring the mass or the quantity of an analyte or a derivative to determine its concentration. Gravimetric methods are analytical techniques used in the food industry to determine the quantity of the specific components, such as the moisture, fat, protein, by measuring its mass. These methods involve isolating the analyte from the sample through processes like filtration, evaporation, or precipitation, followed by drying or burning to obtain a pure form. The weight of the isolated component is then compared to the original sample mass to calculate its concentration. The gravimetric analysis is highly accurate and reliable, making it suitable for quality control and compliance testing. It is commonly applied in determining the moisture content in grains, fat content in dairy, and protein levels in the meat products. Fat analysis by solvent extraction measures the mass of fat extracted from a sample. Fat analysis by solvent extraction is widely used method in the food industry to quantify fat content in various food products such as dietary, meat, and baked goods. This technique involves dissolving the fat in a suitable organic solvent such as hexane or petroleum ether to separate it from the other components. After extraction, the solvent is evaporated, leaving behind the extracted fat, which is then weighed to determine its content. This method is valued for its accuracy and ability to analyze both total and specific fat types. And solvent extraction is essential for quality control, nutritional labeling, and compliance with the food product or the food safety regulations. As content determination measures the residue left after incineration. These chemical methods are essential for providing accurate and reliable data on the composition quality of the food products, widely used in food research, quality control and regulatory compliance in the product development. This is the gravimetric method. It is an analytical method to determine the quantity of an analyte based on the mass of a solid. Here they took a sample and weighed that sample which is to be analyzed, and they dissolved the sample in water. After that, a suitable chemical is added to the water to form a precipitate. After that, filtration is done to collect that precipitate. After that, they done the repeated drying to collect the constant mass of the precipitate. In the types of methods for food analysis, we have subjective, objective and others. In subjective, we have completed the organoleptic. In objective, we have completed the physical, chemical methods of food analysis. Now, we are going to see the microscopic and microbiological methods. In this microbiological methods, we see the plate counts. It determines the number of viable microorganisms in a sample. Next is PCR, which is polymerase chain reaction, which detects and quantifies specific DNA sequences associated with pathogens or the spoilage microorganisms. And next is the microscopy methods. In this we see the light microscopy. It provides detailed images of the food's microstructure. Electron microscopy. It offers high resolution images of the food components. And confocal microscopy. Detailed and three-dimensional imaging of the foods can be seen here. If you like the video, please do like, share and subscribe. Thank you.